Welcome to the year 2026. For decades, the idea of a bipedal, human-like robot was confined to the realm of science fiction and carefully staged, tightly controlled laboratory experiments. But as we navigate through this year, the landscape of robotics has undergone a seismic shift. Humanoid robots have finally stepped out of those sterile research labs. They are now integrated into global supply chains, automotive manufacturing plants, and even everyday domestic settings. If the past decade was defined by the promise of what these machines could potentially do, the current era is defined by widespread, practical deployment. At the very heart of this technological revolution is a highly specialized field of engineering. It serves as the invisible puppet master for every metallic limb, every articulated finger, and every perfectly balanced footstep. This field is known as humanoid kinematics. Kinematics is the branch of classical mechanics that describes the motion of points, bodies, and systems of bodies, without considering the physical forces that cause them to move. In the context of humanoid robots, kinematics is the mathematical translation of the human musculoskeletal system into algorithms and hardware. Replicating the human form is, quite frankly, an engineering nightmare. We humans are inherently unstable, top-heavy creatures. We balance our entire body weight on a relatively small base of support, our feet. Yet, we navigate stairs, we recover from unexpected trips, and we manipulate delicate objects with effortless grace. Teaching a machine made of titanium, aluminum, and copper wire to do exactly the same thing requires solving some of the most complex geometric and physical puzzles in modern engineering. To truly understand how a humanoid robot moves, we must first look at how it thinks about its own body in physical space. This physical awareness is rooted in two fundamental mathematical concepts, known as forward kinematics and inverse kinematics. Forward kinematics is the straightforward calculation of where the robot's end effector, like its hand or its foot, will end up if all its joints are set to specific known angles. Imagine holding your own arm straight out in front of you. If you know the exact length of your upper arm and your forearm, and you know the exact angle of your shoulder and your elbow, you can use basic trigonometry to calculate exactly where your fingertips are located in three-dimensional space. For a robot, forward kinematics is mathematically simple. It is a linear calculation that yields one definitive answer every single time. Inverse kinematics, however, is where the real magic happens, and where the real engineering headaches begin. Inverse kinematics asks the exact reverse question. If the robot needs to place its hand on a doorknob located at specific X, Y, and Z coordinates in a room, what specific angles must the shoulder, elbow, and wrist joints adopt to get the hand there? Unlike forward kinematics, inverse kinematics does not have a single correct answer. Think about how many different ways you can contort your own arm while keeping your hand firmly fixed on a doorknob. Your elbow can swing up, it can drop down, or it can point sideways, all while your hand remains perfectly stationary. In robotics, this means there are multiple, and sometimes infinite, mathematical solutions to a single movement goal. Furthermore, some points in physical space are entirely unreachable, and certain joint configurations lead to what engineers call singularities. A singularity is a point where the underlying mathematics break down, and the robot effectively loses a degree of freedom, which can cause its joints to lock up completely or spin wildly out of control. Modern humanoids rely on incredibly fast, real-time inverse kinematics solvers. These advanced algorithms calculate thousands of potential joint configurations every single second. They constantly optimize for variables like energy efficiency, obstacle avoidance, and overall balance, all before sending the final electrical command to the actuators to physically move. But to move, a robot needs joints, and that brings us to the concept of degrees of freedom. A degree of freedom refers to a specific, independent direction in which a joint can move. In three-dimensional space, a free-floating object has 6 degrees of freedom. It can translate, meaning it can move up and down, left and right, and forward and backward. It can also rotate, which we refer to as pitch, yaw, and roll. The human body is an absolute marvel of mechanical complexity, boasting over 200 degrees of freedom. A human hand alone has roughly 27 degrees of freedom, which is exactly what allows for the astonishing dexterity required to thread a tiny needle or play complex pieces on a piano. Early humanoid robots were stiff and robotic precisely because they lacked sufficient degrees of freedom, often featuring only 6 or 7 degrees of freedom in their arms, and relying on rudimentary, pincer-like grippers. The robots of 2026 have completely rewritten this standard. A prime example is Tesla's Optimus Gen 3, which entered scalable commercial production this year. A significant portion of the engineering complexity in Optimus is focused entirely on its hands, which have been radically upgraded to feature 22 degrees of freedom, closely mimicking human biological capability. To achieve this without making the hands too bulky and heavy, Tesla engineers utilized a tendon-driven architecture. By relocating the heavy actuators, which are the motors, up into the robot's forearm, the fingers are manipulated via high-tension cables. This is very much like how human fingers are controlled by muscles located in the human forearm. This brilliant design significantly reduces the weight at the end of the arm, exponentially increasing the robot's agility and allowing it to seamlessly transition from handling heavy automotive parts to manipulating delicate, fragile components. Conversely, some robotics engineers are using advanced kinematics to push far beyond human biological limitations. Consider Boston Dynamics' all-electric Atlas robot. Completely redesigned from its earlier famous hydraulic iterations, the new Atlas boasts 56 total degrees of freedom. But rather than strictly mimicking human joint constraints, the new Atlas features 360-degree rotational joints in its torso, its hips, and its limbs. By utilizing slip rings that pass electrical currents continuously without tangling any internal wires, Atlas can spin its limbs infinitely in any direction. It possesses absolutely no home position limitation. This unique architecture allows the robot to perform movements that are mechanically impossible for human beings, such as standing up from a flat, prone position by literally folding its legs backward over its own body. By freeing the kinematic model from the rigid constraints of biology, engineers have created a machine that is undeniably humanoid in shape, but completely superhuman in its motion. While articulating an arm is deeply complex, walking is an absolute marvel of dynamic control. Bipedal locomotion is essentially an ongoing process of controlled falling. Think about it. When you take a step, you throw your center of mass forward, temporarily unbalancing yourself, only to catch yourself with your swinging leg just in the nick of time. In humanoid robotics, this complex process is modeled using the inverted pendulum concept. Imagine balancing a broomstick on the palm of your open hand. The heavy head of the broom represents the robot's torso, or its center of mass, and your hand represents the robot's foot. To keep that broom from falling over, you must constantly adjust the position of your hand underneath it. To prevent a bipedal robot from tipping over, engineers rely on the continuous calculation of the zero moment point, or ZMP. The zero moment point is the specific point on the ground where the total sum of horizontal inertia and gravity forces equals exactly zero. As long as the robot's zero moment point remains safely within its support polygon, which is the area outlined by whichever feet are currently touching the ground, the robot will remain perfectly upright. If that zero moment point shifts outside this invisible polygon, gravity wins, and the robot will fall. Historically, older robots used a technique called static walking. They kept their center of mass rigidly over one single foot, slowly moved the other foot forward, planted it securely on the ground, and only then shifted their weight over to the new foot. It was incredibly slow, shuffling, and highly inefficient. Today's humanoids, however, utilize dynamic walking. They intentionally allow their zero moment point to temporarily leave their footprint, utilizing forward momentum to carry them safely through the step. This requires split-second, incredibly dense kinematic calculations. The robot must calculate the precise trajectory of its swing leg, which is the one currently in the air. It must calculate the exact joint torques required for the stance leg, which is the one planted on the ground. And it must calculate the optimal foot placement to absorb the shock of the next step, all while adapting to potentially uneven terrain in real time. But kinematics alone is simply not enough. While kinematics deals purely with geometry and motion, dynamics introduces the messy, unpredictable realities of the physical world, things like mass, inertia, gravity, friction, and torque. You can calculate the absolute perfect kinematic trajectory for a robot's arm to reach out and lift a box. But if that box happens to weigh 50 pounds, that dynamic physical forces will pull the robot forward, instantly changing its center of mass. To bridge this critical gap between theoretical kinematics and physical dynamics, modern robots utilize whole-body control. Instead of controlling the arms, the torso, and the legs as entirely separate entities, whole-body control treats the entire robot as a single, fully interconnected system. If a humanoid reaches out to grab a heavy object, the whole-body control algorithm simultaneously instructs the ankles to flex, the knees to bend, and the hips to shift backward, dynamically counterbalancing the new weight in real time before the robot even lifts the object. Historically, programming these dynamic full-body responses required millions of lines of hard-coded physics equations written by human engineers. Today, the robotics industry has aggressively pivoted toward artificial intelligence, specifically utilizing reinforcement learning in large behavior models. Instead of trying to write explicit, rigid rules for how a robot should walk over a random pile of rubble, engineers now create a hyper-realistic digital twin of the robot inside a physics simulator, such as NVIDIA's Isaac platform or the Newton physics engine. Inside this virtual world, the AI is given a simple goal, such as walk from point A to point B without falling over, and it is allowed to experiment through blind trial and error. Over millions and millions of iterations, simulated at warp speed, the AI naturally discovers the absolute most efficient kinematic synergies on its own. This is exactly how Boston Dynamics taught the Electric Atlas to perform highly dynamic stunts and flawlessly recover from falls. It is also how innovative Chinese companies like Unitree Robotics endowed their highly affordable $16,000 G1 humanoid with the astonishing ability to dynamically stabilize itself even when violently pushed or kicked. The integration of these large behavior models allows robots to completely unify their locomotion and manipulation systems, enabling them to walk, maintain their balance, and actively use tools in continuous, beautifully fluid sequences rather than disjointed, robotic step-by-step actions. Of course, a brilliant kinematic equation is only as good as the physical hardware executing it. The joints of a humanoid robot are driven by actuators, which serve as the machine's muscular system. For many years, the gold standard for high-performance humanoids was hydraulic actuation. The legacy versions of Boston Dynamics Atlas utilized highly pressurized fluid pumped through a network of internal tubes to forcefully move its joints. Hydraulics offered immense power and excellent shock absorption, which is what enabled that early robot to do backflips and parkour routines. However, hydraulic systems are incredibly heavy, they are prone to catastrophic and messy fluid leaks, they are incredibly loud, and they are extremely difficult to scale up for mass commercial manufacturing. The monumental breakthrough that truly enabled the 2025 and 2026 humanoid boom was the perfection of high-torque, all-electric actuators. Modern robots now utilize advanced brushless DC motors paired with harmonic drive gearboxes. These electric actuators offer incredible, micro-millimeter precision for delicate kinematic tasks. They require minimal maintenance, and they run almost completely silently. However, electric gears are rigid. To replicate the crucial shock-absorbing properties of human biological tendons, and to prevent those rigid metal gearboxes from literally shattering when the robot stomps its metal foot onto concrete, engineers employ series elastic actuators and quasi-direct drives. These ingenious systems place a highly calibrated mechanical spring mechanism directly between the motor and the jointed controls. When the robot's foot strikes the ground, that spring compresses, physically absorbing the destructive impact spike before it can reach the delicate internal gears. This mechanical compliance is then fed straight back into the kinematic loop, allowing the robot to actually feel the physical stiffness of the ground beneath it and adjust its walking gait dynamically. But a robot cannot accurately calculate its kinematics if it does not know where its own body is or what its surrounding environment looks like. Therefore, humanoids rely on a continuous, high-speed loop of sensory data, divided into two vital categories: proprioception and exteroception. Proprioception is the robot's internal awareness of its own body. Joint encoders meticulously track the exact micro-degree angle of every single hinge and pivot. Inertial measurement units, which are highly advanced, military-grade versions of the little chips that tell your smartphone which way is up, measure the robot's acceleration and its rotational velocity in three-dimensional space. Force-torque sensors located precisely in the ankles and the wrists measure the exact physical load and strain the robot is currently bearing. All of this internal data is pumped directly into the kinematic solver at thousands of hertz, allowing the robot to tweak and adjust its balance instantly. Exteroception, on the other hand, is the robot's awareness of the outside physical world. This is primarily handled by an array of 3D spatial cameras, LiDAR sensors, and advanced tactile sensors. For a robot to successfully pick up an irregularly shaped object, its vision system must first generate a dense 3D point cloud of the object, identify the absolute optimal grasp points, and then feed those specific spatial coordinates to the inverse kinematic solver. In the absolute newest models of 2026, highly sensitive tactile sensors embedded directly into the robot's silicone fingertips provide essential haptic feedback. As the robot closes its complex 22-degree of freedom hand around a delicate, fragile object, these sensors detect the exact millisecond of physical contact and measure the applied pressure, instantly stopping the actuators before the object is accidentally crushed. All of these incredible advancements bring us to the phenomenal class of 2026, where the convergence of advanced kinematics, electric actuation, and cutting-edge artificial intelligence has resulted in a spectacular roster of commercially viable humanoids actively transforming global industries. Tesla's Optimus Gen 3 is moving aggressively from early prototype stages to massive mass deployment. Tesla fundamentally treats Optimus not just as a traditional robot, but as an autonomous vehicle that happens to have legs and arms. Running on their proprietary FSD version 15 neural architecture, Optimus units are right now performing totally unscripted, autonomous tasks inside gigafactories. The shift of its kinematic actuators to the forearms has given it unprecedented, almost human-level dexterity, allowing it to manipulate flexible wiring cables and delicate battery cells with total ease. Meanwhile, the Boston Dynamics Electric Atlas has entirely abandoned the messy hydraulic spaghetti of its predecessor. The all-electric Atlas is custom designed for intense enterprise applications, specifically targeting automotive manufacturing. Its 56 degrees of freedom and infinitely rotating joints allow it to expertly maneuver incredibly heavy car parts inside tight spaces, with a level of dynamic, whole-body mobility that entirely surpasses human physical limitations. Then we have companies like Agility Robotics with their Digit platform, and Ubtech with their Walker S2. These platforms have definitively proven that practical, applied kinematics can conquer the logistics and heavy industry sectors today. Digit features highly unique, backward-bending bird-leg kinematics. This design choice allows it to squat incredibly efficiently, lifting heavy totes in massive distribution warehouses, seamlessly integrating into tight workflows right alongside human workers. Meanwhile, Ubtech's Walker S2 has advanced its autonomous systems to such a degree that when its battery runs critically low, it uses its kinematic spatial awareness to actively walk over to a charging station, reach completely behind its own back, and autonomously swap out its own depleted battery for a fresh one in under 3 minutes, without any human intervention whatsoever. And we absolutely cannot ignore the massive impact of the Chinese innovators. The rapid global scaling of the humanoid industry is being heavily propelled by Chinese manufacturers moving at breakneck speed. Companies like Unitree Robotics with their highly agile G1, Engine AI with their robust T800, and Astrobot with their incredibly rapid-moving S1 are actively pushing the absolute boundaries of affordable, highly dynamic bipedal platforms. These advanced robots feature up to 29 degrees of freedom in their upper bodies alone, and they actively utilize AI-driven whole-body control to instantly adapt to unpredictable, complex environments in real time. So, where does all of this incredible technology go from here? As we look toward the remainder of the decade, the engineering of bipedal robots is rapidly shifting from simply achieving basic walking stability to mastering extreme energy efficiency and ensuring seamless, safe human integration. One of the absolute largest remaining hurdles in the field is energy efficiency. The biological human body is remarkably conservative with energy. For us, walking requires very little caloric burn, because our biological kinematic structure naturally allows our legs to swing like passive pendulums. Robots, by stark contrast, still expend massive amounts of electrical energy to constantly power their heavy motors and actively maintain their zero-moment point. The next massive frontier in humanoid kinematics lies in what researchers call passive dynamic walking. This involves designing highly specialized mechanical linkages They can naturally swing and step utilizing gravity alone, requiring actual motor power only to briefly push off the ground and maintain forward momentum. Furthermore, as these massive, powerful machines inevitably step out of massive industrial factories and begin working inside human homes, elder care facilities, and crowded hospitals, the concept of safe kinematics will become absolutely paramount. A large robot navigating a cluttered, chaotic living room cannot safely rely on the rigid, uncompromising, and incredibly powerful movements of a traditional industrial robot arm. It must actively utilize compliant kinematics. This means its algorithms must naturally allow its physical limbs to yield softly and safely if it accidentally bumps into a fragile human being or a running pet, all while simultaneously possessing the requisite physical strength to safely assist an elderly person out of a hospital bed. The engineering of these bipedal robots represents one of the most magnificent, awe-inspiring cross-disciplinary achievements in all of modern human history. By meticulously translating the beautiful biological elegance of human physical movement into the rigid mathematical language of kinematics, the physics of dynamics, and the endless potential of artificial intelligence, global engineers have not just created a fancy new tool. They have quite literally birthed an entirely new paradigm of physical automation, one that is quite literally built in our own image, and one that is fully capable of seamlessly inheriting the spaces, the complex tools, and the vital daily tasks of the human world.